Hello everyone. In this video we'll be talking about Hess's law and how you can use Hess's law to solve certain problems where you have a series of reactions that require its use. So you'll be using Hess's law when you have a series of reactions that leads up to a final reaction. So for some reactions we can't automatically calculate what the enthalpy of formation is, because we need a series of reactions to actually get to the reaction we're after. And so Hess's law allows us to do that because Hess's law states that the enthalpy of formation for a final reaction is the sum of the previous reactions, after a little bit of manipulation, and we'll get into that right now. So let's say, hypothetically, you had this reaction here. So let's say you had 3C solid plus 4H2 gas going to C3H8, which is propane. And we want to know the enthalpy of formation for this reaction at standard conditions. So what we'll do is we'll take the series of 3 reactions that leads into this reaction, which you'll always be given, by the way. You'll always be given the 3 reactions that make your final reaction. And we'll write them out and we'll see what they look like. So kind of putting that to the side for right now, we have this first reaction, which is just the combustion reaction of propane, C3H8. I should probably be putting states of matter. This is a gas plus 5O2 gas going to 3 CO2 gas plus 4 H2O. Liquid. And the delta H of this reaction is negative 2,219.9 kilojoules. For the second reaction, we have solid carbon plus oxygen gas forming CO2. And the delta H of this reaction, the enthalpy of this reaction, is negative 393.5 kilojoules. Very straightforward. Okay. And then for our third and final reaction, we have H2 gas plus 1/2 oxygen gas making water. Just like that. And the delta H of this third reaction is going to be negative 285.8 kilojoules. So Hess's law is going to allow us to manipulate these three reactions up here, and by extension these three enthalpies of formation. We can add up those manipulated enthalpies of formation and we can get this answer right here. So what I'm actually going to do is I'm going to rewrite our final reaction below, because that'll help us to see what we need to change. Because it's sort of like a little puzzle where you have to look at what needs to go where and what needs to be multiplied by something. So that might sound a little weird at first, but hopefully it'll become a little clearer. So the first thing I like to notice is what side. So I'm going to pay attention to this final reaction down here primarily. This is what I'm going to base everything off of, because this final reaction is where we need to end up at the end. So I'm going to be looking at this first. I notice that the C3H8 is on the right side of the arrow in our final reaction. But if I come up here, the C3H8 is on the left side of the arrow. So that means that somehow we need to get this C3H8 to the other side of the arrow. And the way we do that with Hess's law is we flip the reaction. There are two things you can do with Hess's law to manipulate reactions. You can flip them in the reverse order, or you can multiply them by a constant. So in this case, since we need that C3H8 on the other side of the arrow, we're going to go ahead and flip this reaction. And whenever you flip a reaction, the delta H changes signs. So this will become a positive. Whenever you flip a reaction, the delta H of that reaction changes signs. It goes from a positive to a negative, or from a negative to a positive. In this case, we're going from a negative to a positive, because we're flipping this equation. Then I notice, so that takes care of the C3H8. But we're going to get that on the right side of the arrow this time. But then I notice that I have 3 carbons in our final reaction. And I notice we have a carbon in this second reaction up here. And it's on the correct side of the arrow. But there's only 1 of them, while we have 3 in the final reaction. So that tells me I'm going to have to multiply this reaction by 3. And since we multiply the reaction by 3, we must also multiply the enthalpy of formation for that reaction by the same number. Okay? So that'll give us that 3C. So that works out. And then the last piece of the puzzle is this 4H2. Well, I notice we have H2 up here in this third reaction, and it's also on the correct side of the arrow, but we only have 1 of them up here, and we need 4. So the easiest way, Occam's razor, is to multiply that last one by 4. And do the same thing to the enthalpy of formation for that reaction. So to kind of illustrate what I'm talking about here, I'm going to rewrite our manipulated reaction. So basically I'm going to flip the first one, multiply the second one by 3, and multiply the third one by 4. And maybe you can begin to see what everything's starting to look like. So if we flip that first reaction, we end up with 3CO2 plus 4H2O going to C3H8 plus 5O2. And like I said, since we flipped the reaction, our delta H will go from a positive, the delta H, which was originally negative, will now become positive. So it started out as negative 2,219.9, but since we flipped it, it's now positive. So for the second reaction, we multiplied everything by 3. So we'll now have 3C plus 3O2 going to 3CO2. And we're going to multiply the delta H by 3. So we'll take our negative 393.5 and we're going to multiply it by 3. Just like that. And then for our final reaction, we're going to multiply everything by 4. So we started out up here and we multiply everything by 4. So we'll end up with 4H2 plus, so 4 times 1/2 is 4 halves, but a simpler way to write 4 halves would be 2, because 4 halves equals 2. So we have 2O2 going to 4 waters. And we'll also multiply this delta H which was negative 285.8 and we'll multiply that by 4. And so now you can see why we did all that manipulation to our 3 reactions, because if we cross out the things that are the same on both sides of the arrow, so for example up here we have a 3CO2 on the left side of the arrow and a 3CO2 on the right side of the arrow, so they cancel. We have a 4H2O up here and a 4H2O down here. They cancel. We have a 5O2 up here, and down here on this side of the arrow we have a 3O2 and a 2O2, and they add up to equal 5. So the 5O2 cancels. And what do you know? We're left with 3C, 4H2O, and C3H8. And that's exactly what we wanted to end up with. So that's the logic behind doing all that Hess's law manipulation. So now all we have to do is add up these 3 numbers. We're actually going to apply Hess's law now. We're going to take the sum of our manipulated enthalpies of formation, and that will give us the delta H for this reaction up here. So we'll take that 2,219.9 and we're going to add that to 3 times negative 393.9, sorry, 0.5, and we're going to add that to 4 times negative 285.8. And this equals, so I'll give you a second if you want to do this in the calculator. Pause the video, feel free. So when you take the sum of these three manipulated enthalpies, you'll end up with negative 103.8 as your final answer. So the delta H of this reaction here is going to, we can erase the question marks now, is going to be negative 103.8, sorry. 103.8 kilojoules. Always, always, always include your units. Cannot stress that enough. Because a number without units is pretty meaningless in terms of chemistry, or any science for that matter. So here we go. This is your final answer.